Assalamu alaikum. So inshallah today we'll be starting lecture 1 in a series of lecture for thermodynamic 1. You can just follow up with me using the slide attached in the first comment under each video. Thermodynamic 1 actually is a conceptual basic course. This is actually the first course in mechanical engineering in the thermal science part. It contains actually some basic fundamental engineering concept, including mainly the first and second law of thermodynamics and their application for different thermodynamic systems. So actually you will benefit the concepts that you will learn here in all thermofluid science, in all thermofluid science courses in mechanical engineering, and also in some other engineering department, and actually also in your engineering work after graduation. So let's start today with just introduction to thermodynamics. Actually, thermodynamic 1, it contains the first 3 chapters. We can consider them as actually introduction to general thermodynamics. We do have chapter number 1 is just general introduction and definition of some basic concept of thermodynamics. Chapter number 2 will be introduction to the different forms of energy and the form of energy transfer and heat transfer. It will be also little introduction to the first law of thermodynamics in chapter 2, and then in chapter 3 it will be also introduction to learn how to use table, especially steam table, and also for gases, ideal and real gases, and how to calculate the properties of any working fluid within any thermodynamic system. Starting from chapter 4, this will be the first law of thermodynamics, the application of the first law of thermodynamics on a closed system. We do have 2 types of system, closed system and open system. We'll see inshallah in this chapter, in chapter number 1, the difference between closed and open system. Chapter 5 will be application of the first law of thermodynamics on open system. Chapter 6 will be the second law of thermodynamics, and then chapter 7 will be application of the second law of thermodynamics to calculate the entropy and the entropy generation within a system. Inshallah today we'll be starting chapter 1, which is actually general introduction to thermodynamics. The chapter title is Introduction and Basic Concepts. If you can just follow up with me with the slides, so let's move to slide number 2. This is the objective of this chapter, to identify the unique vocabulary associated with thermodynamics, including the definition of the word thermodynamic itself, the different types of system, as we said, open and closed system, the state definition of a state of system, a state postulate, equilibrium, process, the difference between process and cycle, and all of this definition will be mentioned, and some other definition also. Also we'll review the difference between a standard system of unit and the English system of unit, and also the dimension of any quantity. I think you know about this, but just let's have a quick revision on this. Also we'll review the concept of temperature scale, and also pressure and the pressure scale, including absolute pressure, gauge pressure, vacuum pressure, and the difference between them, and also the devices that are used actually to measure the pressure. By the end of this chapter, inshallah, we'll just give a kind of on a slide just to introduce a systematic problem solving technique, just to follow up actually while solving any problem while you work actually studying or actually after graduation in your engineering life. Just it's a systematic approach how to solve any problem. Move to slide number 3, which is starting with some definition with the word thermodynamic itself. Thermodynamic is the science that deals with energy, matter, and laws governing their interaction. Energy, which is energy transferring in terms of heat, work, and different kind of energy. And actually matter is the mass whenever we do have mass transfer. So whenever we do have energy transfer, whenever we do have mass transfer, then we can actually apply the governing laws of thermodynamics. The governing laws actually of thermodynamics are mainly the first and second law of thermodynamics. So in general, thermodynamics is a science that deals with energy and matter, and laws governing their interaction, which is the first and second law of thermodynamics. Also, so the word thermodynamic itself, it is coming actually from a Greek word which is divided to 2 words. The word is therm itself, which means heat, and the word dynamics means actually the power, which means actually the science that deals with the conversion of heat into power. Like an example like the car that you are driving. So we do have an internal combustion engine inside this car. Just we burn the fuel to generate a heat of combustion. This heat of combustion just push the piston down inside the engine, so actually it can generate linear motion, and then we can convert actually through a connecting rod this linear motion to angular motion. Then we can have actually distribute this movement to the tires. Then we have actually what we did in this case, just to convert the heat of combustion into mechanical shaft power, into power. So this actually we can consider in this case this internal combustion engine as a thermodynamic system. This system converts the heat into power. And we do have also another thermodynamic system, which is a refrigeration system, which converts actually the power into the heat to control actually the heat transfer, like the operation of the fridge in your home. We will see actually the main difference between all of this, but in general thermodynamics means whenever we do have mass transfer, whenever we do have energy transfer, then we can apply the first and second law of thermodynamics. Energy, the word energy itself is the ability to cause changes. So if you have energy, then you have actually the power or the energy to make any change. If I have energy, I can move from one place to another, I can do my work. So actually this is the definition of energy. Energy transfer is controlled actually by the conservation, what's called the conservation of energy principle, which is coming from the law of mass action, which states that energy cannot be created or destroyed, just it can be converted from one form to another form. And based on the conservation of energy principle, we came up actually with the first law of thermodynamics. Typically it's the same, but the first law of thermodynamics is just applied on a thermodynamic system, which says actually energy input to the system should equal to the energy output plus the energy stored within this system. Based on that, actually energy cannot be created or destroyed. If you look at this example in figure 1, this is the first figure, you can see we do have here a stone that is suspended actually at the top of mountain. It has a kind of potential energy, let's say equal to 10 units, and the kinetic energy in this case is equal to 0, as actually this stone is suspended or not moving. We do have the potential energy. Its definition used, we do have BE for the definition of the potential energy is equal to the mass multiplied by gravitational acceleration multiplied by the elevation. This elevation Z with respect usually to the sea level. So if we do have a stone as we said here, this is actually the elevation Z in reference to the Z level. So this called, when we do have actually any body that is existing at a certain height, it has actually its own potential energy equal to mass multiplied by G, which is gravitational acceleration, which is 9.81 meter per second square. If not given in any problem, you have to keep this value in mind. And we do have the kinetic energy. Kinetic energy, Ke, is equal to half m multiplied by velocity square. V is the velocity, and this is calculated in meter per second, and this is actually the mass in kilogram. Okay. So in this case, this stone has potential energy equal to 10 units, suspended there at the top of this mountain, and the kinetic energy equal to 0 because the velocity is equal to 0. If we let actually this stone to fall down, while falling down, this elevation Z is just reduced. So this means actually as Z is reduced, mass is constant, gravitational acceleration is constant. So this means the potential energy is reducing. While it is falling, it accepts actually velocity. So velocity is increasing. So this means the kinetic energy is increasing. So at a certain position, in the second position, if we look here, if we do have a potential energy equal to 7 units, so in this case, the kinetic energy should equal to 3 units, because actually the total energy is equal to 10 units, and this energy cannot be created or destroyed. Just energy can be transferred from one form, potential energy, into another form, which is kinetic energy, or any different. This is actually restricted to this example. As we said, based on this concept, we can actually draw the first law of thermodynamics, which states, so the first law of thermodynamics is the same actually as the conservation of energy principle, but this is actually applied to any thermodynamic system. So for any system, if you do have input energy, En, so this is E is the energy. Okay, so if we do have energy input to the system and we do have energy out of this system, and part of this energy is stored within this system, delta E of this system, based on actually the conservation of energy principle. So we can come up with the first law of thermodynamic: energy input to the system should equal to the part of energy output plus the part of energy stored within this system. And this is actually the first law of thermodynamic that will be applied inshallah in chapter 4. Then we can look at actually the application of this first law of thermodynamic for closed and open system. Just we'll go for each term and then we'll actually express it actually depending on the type of the system. Anyway, well, this is the general case for the first law, the general statement of the first law of thermodynamics based on the conservation of energy principle. If we move to actually the next slide, you can just look at figure number 2 for this actually fat guy. If we look here, as we said, energy input to the system, if it is 5 units in terms of food or something, then we do have actually exercising and he exerted actually 4 units out of this body. Still we are left with 1 unit that should be actually stored within the body of this guy in the form of fat, and that's why he's getting big. So because actually the conservation of energy principle, energy input should be equal to energy output plus the part of energy stored within the system. Okay. Anyway, fatness is not fatness is very bad. You have to get with your weight down, but it's okay. They are a nice guy. So this is actually the first law of thermodynamic. We say actually first law of thermodynamic, we call it as dealing with the quantity of energy. Just it is an energy balance, quantity N equal to quantity out plus the quantity stored within the system. But we do have another law of thermodynamic which is called the second law of thermodynamic. We'll be speaking actually about the second law in details in chapter 6. But just in brief, second law of thermodynamics deals with the quality of energy, and actually it states for any process it has to proceed in a certain direction from the high energy potential to the low energy potential. So energy cannot transfer from the low level or low quality energy to high quality energy, or it cannot transfer from low temperature to high temperature. Like actually this hot cup of coffee existing at 70 degrees C in a conditioned room, surrounding room at 20 degrees C. So the direction of the heat will be from 70 degrees C to 20 degrees C, not actually the opposite. So second law will say the direction of heat transfer should be from high temperature to low temperature. But if you apply the first law of thermodynamics and you assume the reverse, that heat is actually transferred from the low to the high temperature, just will do have negative sign, but actually first law of thermodynamics will be satisfied because it is dealing with the quantity, not dealing about the logic of the process. So second law of thermodynamics tells you the logic of the process and deals actually with the physics of any process to tell you actually if this process is valid or not valid. Okay? This is the second law of thermodynamics. To study, still we are in this slide 3. To study any thermodynamic system, we do have 2 approaches. One approach is the classical thermodynamic, and the second approach is the statistical thermodynamics. Classical thermodynamic is called also macroscopic approach. Statistical is called the microscopic approach. The difference between them actually is the classical thermodynamic consider actually the average behavior of the system, and this is actually what is required in our engineering life. Usually we need actually what we need is the average behavior of the system. We don't need actually very specific details about this system. Statistical thermodynamics, it's also an engineering approach, but actually it is limited to some application like nuclear reaction. In statistical thermodynamic or microscopic approach, in this approach actually we deal at the individual level. We have actually to measure the property at each individual nucleus, and then we have to integrate through the system to calculate the total property. Like actually this hot cup of coffee. If we want to measure the temperature using the classical thermodynamic, I will just immerse a thermocouple, give me actually an average temperature of this system, and that's it. This is the temperature of the system. But for statistical thermodynamic, in this case, I have to measure the temperature beside each molecule, and then I have to integrate through the whole system to calculate the average temperature. So what we follow actually in this course and all engineering in our engineering life is the classical thermodynamic. We consider the average behavior of the system, but in some application like nuclear reactor, because in this case we are dealing at the nucleus level, because each nucleus has a division reaction and then a kind of a chain reaction, series of reaction. So we have to deal here at each nucleus. So we have to apply statistical thermodynamic, and then we have to integrate to the whole system. If we move to the next slide, we'll see the application area of thermodynamic. Actually, it is hard to imagine that we do have an area that not actually applies thermodynamic laws. So as we said, thermodynamic is applied whenever we do have mass transfer, whenever we do have energy transfer, then we can apply thermodynamic laws in terms of first and second law of thermodynamics, and then we can calculate the energy transfer through the system, and we can calculate also the efficiency of this system. Here in this example, we do have actually this house. We do have sunlight is coming down. It can be absorbed by solar collectors. Then we can absorb the heat. This heat can be used to heat up some water, so we can have actually a kind of hot bath. So in this case, we do have heat transfer, which is a kind of energy transfer. Then we can apply the thermodynamic law, and we can calculate the amount of heat. In airplane, we do have actually a jet engine. So we burn the fuel in order to have actually a thrust moving force to move this airplane. And also in a boat or something, usually we do have a diesel engine, like the engine in your car. But usually the engine in your car is a kind of a spark ignition engine, but this is a kind of diesel engine, however the same design. So we burn the fuel to have a mechanical shaft power to move this boat. The other application, we said thermodynamic is the conversion of heat into power. To actually we burn the fuel or something to can get mechanical shaft power. Another application is the conversion of power into heat. Like in case of a fridge, actually we absorb the heat from the low temperature inside the fridge and reject actually this heat to the high surrounding air, to the high temperature in the surrounding room. So in this case I need to absorb heat, move the heat, or actually have heat transfer from the low temperature level to the high temperature level, and this is actually based on thermodynamic is not possible. So in this case what we should do, actually we have to pay work on this system. We do have in this case, in case of fridge, we do have a compressor that is connected to an electric motor, so we do have electrical power is coming into to drive actually this compressor in order to be able actually to absorb the heat from the low level to the high level. Okay, this is also application of thermodynamic. Our human body actually itself is also can be considered as a thermodynamic system. Our body has a temperature if we are existing in this air-conditioned room. So in this case, actually, we do have heat transfer from our body to this actually cold air around us inside this room. Also, we do have mass transfer. We can eat food, and also we do have exit. So we do have both mass and heat transfer. So our body is a thermodynamic system. And actually, we do have many applications. As we said, it is hard actually to imagine a system that does not actually relate to thermodynamics. Let's move to another topic, which is introduction to dimension and limits. So for the dimension, we do have three basic dimensions, and from those three basic dimensions, actually we can generate the dimension of any other quantity. So we do have the basic dimension mass has a symbol m, and we do have the basic dimension of length or distance, which is L, and also for the time it is small t. And in some cases for heat transfer we consider the dimension for temperature to be as theta. Okay, to generate actually from those basic dimension, we can generate the dimension of any other quantity. Let's consider the velocity. Velocity, its definition is actually distance cut per unit time. So the dimension will be distance or length is L divided by time, which is t. This is the dimension, and the unit is, in this case, let's consider the SI system of unit. So in this case, the unit of this velocity, distance is measured or calculated in meter and time in seconds. So its unit in the standard system of unit is meter per second. Because we do have another system of unit, which is the English system of unit. So for the English system of unit, we do have the dimension in this case. Usually the distance is calculated in feet, and time is the same in second. We will see the relation between feet and meter. We will just show you how we can convert it from meter to feet. Let's consider another parameter like acceleration. acceleration, which is A, has the symbol A, is defined as the rate of velocity v over t. So the dimension will be L over t like velocity divided by 1 more t, so it will be L over t square, and the dimension is meter per second square. Okay. The force, another example. Force is defined as mass multiplied by acceleration. So mass multiplied by force has the symbol F and is defined as mass by acceleration. Mass, the unit of mass, the dimension of mass is m. Acceleration is L over t square. Okay, and the force actually mass, the unit of mass is kilogram. Distance or acceleration is meter per second square. Kilogram meter per second square is equivalent to Newton. So we do have 1 Newton is equal to 1 kilogram meter per second square. Another parameter, if we do have work, the work is equal to force applied to move actually a certain body a certain distance. So force multiplied by distance. So in this case the unit will be the unit of force, which is ml divided by t square multiplied by distance, so this will be L square. Force is the unit of the force is Newton multiplied by distance, which is meter. Newton by meter actually representing joule. So we do have 1 joule is equal to 1 Newton meter. Power of the system, if we need to calculate the power of the system. Power is the rate of work done, so work per time. Work is force by distance. Distance divided by time will be velocity. So the power is defined as the force multiplied by the velocity. So the dimension in this case will be the dimension of force, which is m L divided by t square multiplied by the dimension of velocity, which is L divided by t, so this t will be tq. And in this case the power will be actually the unit of the work per unit time, so it will be joule per second. And we have joule per second is equivalent to watt. So we do have 1 watt is equal to 1 joule per second. Let's consider one more parameter. Let's consider here the pressure. Pressure B. Pressure is defined as the force per unit area. Okay, so the force in this case, the dimension of the force is ml divided by t square per unit area, so it should be L square, so the square will go with L, so it will be m equivalent to m divided by L multiplied by t square. And the dimension or the unit of the pressure in this case, force is calculated in Newton, and the area in meter square. Newton per meter square actually is equivalent to Pascal. So we do have 1 Pascal is equal to 1 Newton per meter square. Okay. Actually we do have different important unit actually for pressure, and also in the English system of units. Those are actually the unit in the standard system of unit. If we do have a small value of velocity or acceleration or something, we can use actually the normal unit. Let's say we do have a small value of force, then we can actually express this value in Newton. But if we do have higher value, then in this case we do have, if you look at table 1-2, you will see here we do have, we can express actually this value in kilo. We do have 1 kilo. Let's say 1 kilo Newton is equal to 10 to the power 3 Newton. So in this case we can multiply by 10 to the power 3. If we do have big value here of force, then we can express actually this number in kilonewton, and we do have 1 kilonewton is equal to 10 to the power 3 Newton. If you look at table 1-2, we do have also, in addition to kilo, we do have mega. 1 mega is equal to 10 to the power 6. We do have giga. 1 giga is equal to 10 to the power 9, and so on. You can look at actually this table to configure about this. Okay. This is in what's called the standard system of unit. If we move to the next slide, which is slide number 8, you will see here we do have another system of unit, which is the English system of unit. This unit actually is applied mainly in United Kingdom and also United States. So if you do have something, if you are working outside in your engineering life after graduation, and if you do have exporting a kind of tubes or getting actually a device that is coming from UK or US, so in this case you will see actually the unit are expressed in the English system of unit. In this system of unit, if we look at this slide, the distance is calculated in feet instead of meter, and we do have in this case 1 feet is equal to 0.3048 meter. And also in this case the mass is calculated in what's called bound mass, and we do have 1 bound mass is equal to 0.45 something kilogram. It's about half kilogram. Actually, you don't need to remember those values. If you do have a problem or something while practicing or something or in your exam, you will actually provide those values. But actually, this is for from the English system of unit to the SI system of unit. But if we do have, let's say, values expressed in kilonewton or something, this will not be mentioned. This is actually, you have to know that 1 kilo is equal to 10 to the power 3, and you have to know about those values. But if the units are in the English system of units, then you will be just provided actually those conversion value. You don't need to remember, but they are simple and you can just keep in mind. Also, we do have the force in the English system of unit is measured in what's called pound force. And if you look at this slide, we do have 1 pound force is equal to 32.174 pound mass feet per second square. Can we convert from pound force in the English system of unit to Newton? So we do have this equation, 1 pound force is equal to 32 point something. Bound mass, we can just remove bound mass and just substitute by 0.45 something kilogram and multiply this, just remove feet and just multiply by 0.3048 meter, and it will be actually 32.174 multiplied by 0.45 multiplied by 0.3048 kilogram meter per second square, which is Newton. So we do have 1 pound force is equal to 32.174 multiplied by 0.45 multiplied by 0.3 Newton. And this is actually the conversion from pound force to Newton. We do have also the work is calculated in joule in the SI system of unit. However, in the English system of unit, we do have calorie. We do have 1 calorie is equal to 4.18 joule. And also we do have another unit which is BTU. BTU is the British thermal unit, is equal to 1.055 kilojoule. And actually, I think you have to remember this conversion, important conversion from calorie to joule. We do have 1 calorie is equal to 4.18 joule. Okay, just the last thing to mention here, something important about pressure. We said pressure is calculated in Pascal in the SI system of units. There is also another unit for the pressure, which is called actually bar. We do have 1 bar is equal to 10 to the power 5 Pascal, or equal to actually 10 to the power 2 kilopascal. We do have also 1 atmosphere, which is actually our atmospheric pressure, equal to about 1.05 bar. So usually we do have 1 bar, and this is actually the definition where the definition of bar is coming from. It's actually related to the atmospheric pressure. So usually we do have 1 bar is almost equal to 1 atmospheric pressure. And 1 atmospheric pressure is equal to 10 to the power 5 Pascal. You have to keep actually those values in mind. In the English system of units, they use actually another unit for pressure, which is called actually PSI, which is actually pound per square inch. We do have 1 bar is equal to 14.5 pound per square inch, or PSI. If you went actually to the puncture or something to fill the car tire, to increase the car tire pressure, so in this case you will find actually the scale there has 2 scales. The measuring unit, the device that is measuring pressure, has actually 2 scales. One scale is in bar and one scale in PSI. Usually you have to set this value to a kind of 35 PSI. 35 PSI, which is the car tire pressure. 35 PSI is almost equal to around 2 bar, 2.5 bar. So usually you have to set actually the value of the car tire pressure. You have to set it to around 2.5 bar or around 35 PSI. PSI means actually pound per square inch, and this is actually the unit used to measure or to calculate the pressure in the English system of units. Okay. Before we close about this brief introduction about dimension and unit, let's define another important actually property of the system, which is the weight Weight is defined actually as the mass multiplied by gravitational acceleration. We do have another property which is called the specific weight. The specific weight